glucose is eventually converted into the glycogen, which we'll talk today. Okay, and these are the two major things we like to talk, and then the regulation. We discussed other day that gluconeogenesis, synthesis of new glucose, is kind of reverse of glycolysis. Correct? So in glycolysis, you have glucose, it goes all the way to 2 molecules of pyruvate, and in the gluconeogenesis, pyruvate is converted into glucose. But for the PCA cycle, pyruvate gets converted into acetyl-CoA. I was trying to look for literature, and most of the literature says that acetate unit, 2-carbon unit, cannot be converted back to glucose directly. So that means if we consume a lot of fat, it's not going to give immediately glucose if we are in need of glucose. But that acetyl-CoA, 2-carbon unit, can get into other pathways and eventually contribute to the net synthesis of glucose via formation of other intermediates. Okay, so it's not totally no that you cannot make glucose out of acetyl-CoA or out of fat, correct? Fatty acid is degraded to acetyl-CoA. That acetyl-CoA although does not go back to glucose directly, but there are other way around. Some of the acetate still could be converted into glucose. So if you can make pyruvate from any other molecule like lactate, we discussed other day, lactate or lactic acid is produced as a function of incomplete combustion of glucose, correct? Low oxygen or hypoxic burning of glucose, you produce lactate with the help of lactate dehydrogenase. Excuse me. So this lactate is released into the bloodstream, it goes to the liver, and in the liver, lactate gets oxidized to pyruvate. Pyruvate go back to phosphoenol pyruvate and so on and so on. We discussed the detailed pathway. So there are two new reactions where pyruvate is converted into phosphoenol pyruvate. One is pyruvate carboxylate, another is phosphoenol pyruvate carboxykinase. These two, especially this first one, is a driving force, correct, for initiating the gluconeogenesis. So there are two kind of reverse pathways, so both cannot go at the same time. If the cell is low in energy, you turn on the glycolysis, but if cell is high in energy, including acetyl-CoA, correct? High acetyl-CoA is a correct indication of high energy cell. So if acetyl-CoA, shift rate, all these things are high or ATP is high, then you convert this pyruvate, you turn on this pyruvate carboxylate and turn off the hexokinase. Does it make sense? So depending on the need of the cell, either it can go forward, back down, or go backward to make the glucose. Insulin, correct? The goal of insulin to decrease the glucose concentration, correct? So it turns on the glycolysis, turn off gluconeogenesis. Because if you turn on gluconeogenesis, you will increase the glucose level. Does it make sense? So you slow down, inactivate, insulin inactivate the pyruvate carboxylate. Whereas glucagon or the epinephrine does the reverse. Epinephrine would or glucagon try to maintain the net blood glucose level, correct? So one way it can maintain is making some glucose from pyruvate to glucose. That means it turns on the gluconeogenesis, it activates pyruvate carboxylate. glucagon and epinephrine. Does it make sense? Again, also it will break down the glycogen into glucose. So these pathways you try to fit in your brain. So tomorrow's talk actually is going to be biochemistry studies the fat metabolism. There's something called white adipocytes, white fat, and another is called brown fat. Okay, brown fats are better than white fat because brown fat could be burned easily. Okay, because the lipolysis goes on, and white fat does not like to burn easily. If you exercise, your brown fat increases. If you don't exercise, your white fat increases. Does it make sense? So there is interesting connection, and those are all connected. They are not separate. Fatty acid metabolism, glucose metabolism, they are all connected because net goal is the energy of the cell, correct? Energy making and energy expenditure, correct? So fatty acid biosynthesis, fatty acid degradation, they are all linked to energy expenditure. So attend, I think it will be interesting for you, and ask some questions. Okay, so it says fatty acids, substrate for gluconeogenesis, fatty acids cannot. Why? Most fatty acids in acetyl-CoA cannot provide net synthesis of sugars, but there is walkway around. Cell does metabolize some of the acetyl-CoA into glucose to other pathways, not directly converting into pyruvic acid. Whereas pyruvate, lactate, glycerol, amino acids, and all TCA cycle intermediates can be utilized. Think about this. All TCA cycle intermediate can be utilized, then why not acetyl-CoA? Does it make sense? Because acetyl get into the TCA cycle. So you still, although it does not go directly back into glucose, but they can get into TCA cycle intermediate, so you still can make glucose out of it. So all these are substrates. How do you think glycerol gets into the gluconeogenesis? Correct? Glycerol has this. This is your glycerol. You can glycerol kinase, and you can oxidize. You will produce phosphoglycerate. Correct? So you can make the intermediate for the feeding up gluconeogenesis. Does it make sense? Okay, so amino acids can also be converted. So when we talk about insulin resistance or diabetes, correct? We cut down the carb, but we keep eating a lot of fats and protein. That's also not good, correct? Because eventually proteins could also be converted into high glucose level. So cutting down the amount of food intake, exercise, healthy lifestyle is very critical, whether it is a fat metabolism or diabetes or cholesterol. Okay, so let's go. We discussed the chemical reactions. The steps 1, 3 and 10, 1, 3 and 10 are regulated steps. 1 is the pyruvate carboxylase, correct? First one is the pyruvate carboxylate that's regulated, and then is the phosphatate, glucose 6-phosphate to glucose, correct? So you have a phosphatate all here regulated state. The pyruvate carboxylates, know the mechanism. You read ATP and biotin. And biotin is the cofactor which normally linked to the active site of enzymes, lysine. Acetyl-CoA is an allosteric activator. Why? Why acetyl-CoA is an allosteric activator for pyruvate carboxylate? Does it make sense? Why? Why it is an activator?
Because you have a lot of it.
Yes?
If you have a lot of it, you're breaking down a lot of sugar.
Yeah, so your cell energy state is high, because and that's why you want to minimize, remove the acetyl-CoA. So you activate one of the pathways, make some glucose. Correct? And the glucose can be stored in the form of glycogen. So it is an allosteric activator. Mechanism is typical of biotin. I did not go over, but I can ask in your exam. Correct? Regulation when ATP or acetyl-CoA are high, pyruvate enters into gluconeogenesis. Is it clear? We did these reactions last class. Glucose 6-phosphatase and fructose 6-phosphatase, these are the reverse of the kinase reaction in the last two steps, and those are also unique to the gluconeogenesis. Rest of the stuff is same. Lactate recycling, we kind of discussed that vigorous exercise can lead to build-up of lactate and NADH due to oxygen shortage, hypoxia, and need for more glycogen. So you need energy, correct? So you need, even if you produce NADH, you still can make energy, correct? Through oxidative phosphorylation. So NADH can be oxidized, deoxidized during the reduction of pyruvate to lactate. Lactate is then returned to the liver where it can be deoxidized to pyruvate by again the same enzyme, liver lactate dehydrogenase. So this is a reversible enzyme. Most of the dehydrogenase, oxidoreductase class of molecules, correct? These are just electron transfer reactions, correct? So they can be reversible. What type of active site these enzymes have? What is the cofactor you think they need? Dehydrogenase. NADH is one of the cofactors, yes, NAD or NAD plus or NADH. What other cofactors? FAD, but what other? What typical of these oxidoreductase? How do they facilitate the electron transfer? What they are made of? No idea. Normally, these oxidoreductase family of enzymes has a metal cluster along with their co-activators. Okay, their active site has many metal ions, and those are normally the transition metals. Correct? Copper, manganese, iron, cobalt. Correct? Copper, manganese, iron, these are the most common you see, and these are copper sulfur cluster, iron sulfur cluster. Anybody who works in Dr. Pierce's lab? Yeah? No? We have Dr. Pierce. He studies these complex metal enzyme properties. Those are extremely complex because this is metal sulfur cluster. So that's why the same enzyme is able to give electrons and take electrons, so they can stabilize both transition states. Does it make sense? That's why we need some kind of transition metal ion for our body to function. So once liver converts this lactate to glycogen, this glucose is now recirculated to liver for exercise and then reprocessed lactate into glucose. So these are all the regulations we discussed. When glycolysis is turned on, gluconeogenesis is turned off. When energy status of the cell is high, glycolysis is turned off, correct? And molecules should be used for the synthesis and storage of glucose. Correct? Energy status is high, you make glucose, also you make lipids. Correct? Lipid biosynthesis, because you don't need high acetyl-CoA sitting in the cell. You convert to either glucose, which will be glycogen, or you make it to lipid so that it will be stored in the form of fat. Does it make sense? These are the reverse of degradation. Glucose should be rapidly degraded to provide energy when energy status is low. Low energy status means high concentration of AMP, low concentration of ATP, correct? Low acetyl-CoA, low citrate, and all these metabolites. The regulated steps of glycolysis are the very steps that are regulated in the reverse direction, because those are the places you can really control this way or that way, correct? So read these basic and try to process in your brain. Sometimes I get lost and wait for some time to process what direction it is going. This is a kind of regulation of gluconeogenesis. Fructose 2,6-bisphosphate, negative regulator. Why? Why fructose 2,6-bisphosphate negatively regulates or inhibits gluconeogenesis? Why?
Because it's an activator in their direction.
Activator. So what does it activate? Phosphofructokinase, PFK. So it is a huge regulator for fructose 2,6-bisphosphate synthesis and activation of phosphofructokinase, which converts fructose 6-phosphate to fructose 1,6-bisphosphate, correct? PFK. So 2,6-bisphosphate is a negative regulator here, positive regulator here. AMP negative, it's obvious because low energy. Does it make sense? Acetyl-CoA is a positive regulator. It is correct. High energy state of the cell. So you want to remove acetyl-CoA, make glucose. Does it make sense? So basically all of these factors activate pyruvate carboxylase. That's the first enzyme. All of these factors will also activate. What is the other enzyme? The acetyl-CoA carboxylase. Does it make sense? Because they all are involved in removing acetyl-CoA from the cell. Does it make sense? Okay. So these are the regulations in your exam. I will ask which of the following, correct? Actually positive or negative regulators.
Did you say
No, this one. Acetyl. These are low energy states of the cell. They will be negatively acetyl-CoA carboxylate. So, as long as it fits to your brain thinking what is right for the cell, that's what you try to get. Fructose 1,6-bisphosphatase is inhibited by AMP. Fructose 1,6-bisphosphatase is inhibited by AMP. Does it make sense? Fructose 1,6-bisphosphatase. This is the second to last enzyme. Correct?
Yeah.
So AMP means high AMP means low energy state of the cell. So you want to inhibit the gluconeogenesis as a turn on the glycolysis. Does it make sense? So it's a negative regulator. Activated by citrate, reverse of glycolysis. So these are common sense. Fructose 2,6-bisphosphate is an allosteric inhibitor of this phosphatase again. Correct? Both acetyl-CoA pyruvate carboxylate and the phosphatase are major regulatory, and all the regulators, these are basically metabolites in the cell. This is called feedback loop. The product or intermediate in a biosynthetic pathway regulate the enzymes involved, so that when cell senses that there is high concentration of the energetic molecules, you don't need. So they themselves act as allosteric inhibitor or activator to turn on or turn off the pathway. And normally turning on or turning off takes place by what? What do you mean by turning on an enzyme? What does it exactly happen? Let's say turn. One of the things is that phosphorylation, correct? So if you say that phosphorylation of 1,6-bisphosphatase, it's an phosphatase, it's inactive. Upon binding this, it's slightly deactivated by removing the phosphate. Normally, phosphorylation activates. Not always. There are some phosphorylation which inhibits. So phosphorylation is one, correct, which is most well studied, phosphorylation. But there are many other modifications which turns on the enzyme and turns of the enzyme. Those are mostly not studied. That include methylation, acetylation, lipid modification, and many others. Now that we understand the gluconeogenesis, we have made glucose from acetyl-CoA, the pyruvate acid. Now, how is glucose stored in the form of glycogen? From BIOCHEM 1, you know that glycogen is nothing other than composition of two forms of polymer, amylose and amylopectin. Correct? 10 to 30% amylose in starch and 70 to 90% amylopectin. What is the difference between amylose and amylopectin?
The bond.
Yes?
It's like the bond is like alpha 1,4 versus alpha 1,6.
No, all of them has alpha 1,4.
The amylopectin has alpha 1,6 linkages.
Linkage, this branch. Correct? All of them, linear chain is alpha 1,4. The branch is the alpha 1,6. So amylose is alpha 1,4, reducing the amylopectin and branches every 12 to 30 SCD. What is the difference between starch and glycogen? Yes,
Glycogen is an animal and starch is plant.
that is true, but structurally.
Oh.
That's true. Glycogen is in animals, storage polysaccharide. Starch is a plant, storage saccharide. What is the difference between structural difference or chemical difference in terms of starch and amino acids? I mean glycogen. The degree of branching. Okay, glycogen is more packed. The branching is more frequent compared to starch. Here is your amylose. Amylose linear chains of glucose alpha 1, 4, and this is alpha or beta. This linkage. This is a branch chain. Alpha beta.
Alpha.
Whom should I believe? This is branch, correct? These are glucose. So it is alpha or beta? Alpha, beta. So alpha beta is in terms of what? How do you differentiate? What are the alpha and beta? Huh? Anomeric carbon, that's good. Correct? Anomeric carbon, which is a carbon which forms from cyclization of the sugar. What is the anomeric carbon in this molecule? Is this anomeric carbon?
Yeah.
This one?
Carbon.
This is the anomeric carbon. So as soon as you say glucose, this is fixed. It is not alpha or beta. Alpha and beta is here. Now how do you differentiate alpha and beta?
Beta's on top.
Beta is up and alpha is down. That's not so nice. You turn on the molecule, correct? The groups in the bottom will go up. Does it make alpha beta? So how do you make alpha beta? How do you, this molecule is alpha or beta?
What side the last chiral hydroxy group is on?
Exactly. So you compare this particular group and this particular group. If they are in the opposite phase, correct? They are alpha, and if they are in the same phase, this is beta. So this is the anomeric carbon of the one glucose. So this is alpha 1, and this is the 4th hydroxyl group of the second glucose. Sorry, not 4. This is the 6. 1, 2, 3, 4, 5, 6. 6 hydroxyl. So alpha 1, 6 linkage. And this linkage in glycogen is more often. So here it is alpha 1, 6 linkage. What is some properties of these glycogens and starch in terms of when they absorb some iodine? If you take, yes, you want to discuss something?
I said the amylose will give a dark blue, purple.
Dark blue color. Why?
The Ki, potassium iodide, how do you call it?
Potassium iodide.
Yeah, it reacts with the starch.
So the iodide. So when these molecules, the starch molecules, correct, when dissolved in water, they form kind of helical micelle. Helical type of micelle, and the iodine gets trapped inside. In fact, how many of you eat white rice boiled? Boiled white rice. I think less or more, almost everybody eats some amount of rice, correct? If you eat this boiled white rice, normally I do. I put a little bit of iodized salt and 1 drop of lemon. Okay. You see, when you put the lemon, on this white rice, you can actually see this bluish light. Sometimes you have to imagine that. That there is blue color. But you do see bluish tint of fluorescence comes out. Now, why you need to boil the rice? Starch, that's a good answer. Correct? So when you boil, why starch gets into solution? It does not break down. It does not break down. What is special about glucose? What is the special property? They have lot of these hydroxy groups. Correct? It's a highly polar surface. Right? As soon as they get close to water, they absorb the water, they swell. That's the rice. When you boil, they swell. And once they swell, they make lots of holes so that enzymes can easily access. Right? So that's one of the advantages not taking unboiled rice, because enzyme cannot access. You boil it, right? So that enzyme can hydrolyze or phosphorylate the glycogen or starch into glucose. So branching in starch is less frequent than glycogen, and glycogen is polymeric, or glycogen or starch, the polymeric molecule gets broken down into glucose 1-phosphate with an enzyme phosphorylase. It's not a hydrolysis, rather phosphorylasis. Right. So you have this type of structure. Correct? 1, 4. So I'm not drawing the left. So this is your glycogen, I think. Correct? Your hydrogen. This is the glycosidic linkage. It gets phosphorylated. Phosphorylase is the enzyme which hydrolyzes this, releasing your glucose 1-phosphate type of. So it's not a hydrolysis reaction, it's a phosphorylasis reaction. So the phosphorylase releases glucose 1-phosphate from the amylose or amylopectin chains, and this glucose 1-phosphate gets into the glycolysis and gives the energy. Branches provides higher packing and higher source of, when they are hydrolyzed, they give lot more glucose molecules from the same unit. Here is the phosphorylasis reaction. Phosphate attacks this one, hydrolyzes this glucose 1-phosphate, which enters into the glycolysis and vicious cycle. So start phosphorylase reaction cleaves glucose residues from amylose. The enzyme also called amylase because it hydrolyzes the amylose. Does it make sense? So amylase actually phosphorylase releasing glucose 1-phosphate, which gets into the glycolysis. So glycogen is Glycogen is similar to starch. Almost 10% of the liver mass, 1 to 2% of the muscle, because your muscle is rapidly exercising. It needs a lot of glucose, correct? So that's why if there is a glycogen, it gets hydrolyzed. Liver also does a lot of glucose needs. And glycogen is stored form of energy in the animals. Only difference from starch is number of branches. Alpha 1 6 branches every 10 to 8 to 12 residue versus 12 to 30 residue in starch. Those are some basic things we want to know. Now, next we want to understand how glycogen is produced from glucose. So, the way glycogen is produced, you need to synthesize. Basically, you have to assemble the glucose molecules. You have to synthesize this glycosidic linkage, correct? So that normally does not happen. No biological reaction occurs without activation. No biological reaction happens without activation. So you have to basically activate the glucose molecule so that 4th hydroxyl group from another glucose can act as a nuclear backup. Right? So this is glucose 1 phosphate. It has to react with another glucose molecule. This is 1, 2, 3, 4th hydroxyl group has to react. Correct? So this hydroxyl group has to react on this and do this particular reaction. But this does not happen normally because this phosphate is not a good living group. Does it make sense? So you need to somehow make this group as a good living group, basically activate. And the way activation takes place is very similar to the we saw in lipid head group synthesis. Okay? Again, the glucose 1 phosphate reacts with UDP, reacts with UTP, and this forms UDP glucose. It's for just nothing other than activation. So it reacts with, so this is not going to work. So you use an UTP. This is your UTP. This phosphate group here forms UDP glucose. Right? So from here we produce this molecule. Okay, now it's a pretty good living group because you neutralize the charge And now this hydroxyl group can, the fourth hydroxyl group of the glucose, right, can attack this and makes this glycosidic Does it make sense? Again, you have this group can react, or this hydroxyl group can react with other UDP glucose. So basically what we are telling that glucose 1-phosphate is a starting material for glycogen synthesis, and that glucose 1-phosphate reacts with an UTP to form UDP glucose activated. You see a anhydride linkage here, right? Normally it's not the way I draw, it is a kind of nucleophilic substitution, correct? SN2. But normally it's not true SN2 reaction, it goes via kind of SN1. So this group is lost, you form a kind of positive charge, carbocation, flat surface. Now this hydroxyl group can attack from both ends. Does it make sense? But it attacks from the alpha end just because this is an enzymatic reaction. Enzyme can control the stereo specific or stereo selective manner, correct, to form the right type of bond. So once you form this one, this reacts with a new glucose molecule attacks here. So you see again the UDP, uracil triphosphate, correct? UTP is not only part of the ribonucleotide triphosphate, it is also critical for activity in several types of biomolecules, correct, for biosynthesis. So here you see that UDP glucose lost this molecule, you form a carbocation type. What type of hybridization this carbon has? Anomeric carbon there. After losing this positive charge, what is the hybridization? State of hybridization. sp2. What is special about sp2? It's planar, flat, correct? So nucleophile can attack from bottom or it can attack from top, correct? But in this case, it attacks from the bottom alpha phase because of the enzyme specificity, and maybe there are other glucoses. So eventually makes only alpha 1 4, not beta. Does it make sense? So this is the enzyme which is involved here. It's called glycogen synthase, GS. Glycogen synthase. Alright? Again, it's a very important enzyme, and like other metabolic enzymes like pyruvate carboxylase, like acetyl-CoA carboxylase, glycogen synthase must be regulated, correct? This regulation is influenced by all these factors which control other metabolic enzymes, insulin, glucagon, epinephrine, correct? All these regulatory enzymes. Phosphorylation of glycogen phosphorylase. So glycogen phosphorylase and glycogen synthase. Glycogen phosphorylase is the enzyme which hydrolyzes glycogen. not hydrolysis. More specifically, it phosphorylates. It makes glucose 1 phosphate, right? To make monomeric glucose. So, glycogen synthase combines glucose 1 phosphate to form the polymer. So, these two, glycogen phosphorylase and glycogen synthase, are the reverse enzymes, and they must be regulated, correct, in a reciprocal manner. Very interesting stuff. Phosphorylation causes amino terminals of the protein, correct? Basically, what I want to say, phosphorylation controls the activity. 9 serine residues on glycogen synthase are phosphorylated. That phosphorylation activates. Does it make sense? GP, GS, glycogen phosphorylase, glycogen synthase, hormone glucagon, epinephrine, activate adenylyl cyclase. What is adenylyl cyclase? It is critical for making the cyclic AMP. Adenylyl cyclase is an enzyme which converts ATP into cyclic AMP. Cyclic AMP is a signaling molecule. It's a second messenger. Okay. It controls lot of signaling pathway. I'm not going into detail, but it's a very important signaling molecule. As soon as you are stressed, your glucose, your cortisol level is high, your some part of the brain starts to activate adenylyl cyclase, makes cyclic AMP, it turns on a lot of the signaling pathway. So it's a kind of somewhere cyclic AMP level actually tells that there is something emergency going on. Does it make sense? So these hormones control the adenylyl cyclase. Cyclic AMP activates kinases and phosphatases that control phosphorylation of GP and GS. Does it make sense? So cyclic AMP concentration controls the phosphorylation, that means activity of glycogen phosphorylase or glycogen synthase. So phosphorylation, dephosphorylation is a major switch in many situations. Metabolic effects of insulin. Now, by now you know, correct, what insulin does. Correct? So you have insulin receptor. So insulin receptor is a kind of membrane, transmembrane protein. Once insulin is what? It's a peptide protein. There are two proteins, correct? Insulin has two peptides, they are disulfide linkage. One is I think 29, another is 21. 29 or 30, I don't remember. Okay. So this is your insulin, two peptides. So these two peptide containing insulin bind to this receptor. This is called insulin receptor. Expression of insulin receptor is critical for insulin signaling. Right? If our body is not producing insulin enough, you will have problem in glucose metabolism, which is type 1 diabetes. But type 2 diabetes, body produces insulin, but tissues are not sensitive enough. Adipose tissues are not sensitive enough to insulin. It could be possible that this receptor is not able to recognize insulin. Or it could be there are many other downstream signaling players here which are defective. We have insulin, but it's not functioning. Tissues are not sensitive. Adipose tissue, which is highly insulin sensitive, muscle tissue, which is highly insulin responsive, brain, correct? They also consume a lot of glucose. They have insulin receptor. Primarily the adipose tissue is not so sensitive. Anyway, the receptor get phosphorylated and initiate the signaling cascade. Protein phosphorylation, second messenger, including cyclic AMP, is produced. Now, insulin negatively regulates glucose variation. Does it make sense? Negatively regulates protein breakdown, lipid breakdown. Does it make sense? Positively regulates lipid biosynthesis, positively regulates glycogen synthesis, that means glycogen synthase is active, glycolysis positive. These two we have not discussed. So this is what I want to get from you, that you understand. We are consuming some lipids or fat, correct? Because fatty food is tasty, we just, correct? If sugar is very tasty, so we just take it. Valentine's Day, correct? Lots of candies around, so keep consuming. But how your body is handling, that's the most difficult part. So now I think you understand already how these lipids, what we take, is metabolized by the body, correct? How the lipids are metabolized. So this is what we have to get from this class. I think this is the end of this. Insulin secreted from the pancreas. It is directly connected to the liver. Response can increase blood glucose. Insulin has many other effects beyond the sugar metabolism. Okay. So, hormonal regulation, opposite to insulin, glucagon, 29 residue, peptide secreted again by pancreas. Look at pancreas is so important, correct? Organ. Actually not a big, tiny amount of cell population, which is called beta cells. It's not a lot. It produces insulin. And if this population of cell is lost, we are in big trouble because there is nobody. Right? So there is no other mechanism by which you can supply insulin other than injecting insulin. There are a lot of other drugs. Can you name a drug beyond insulin for the treatment of diabetes? No? No, you are not in that stage yet, I understand. Right? But in my stage, I need to know, is it a good or bad? Correct? I am not diabetic yet, but somewhere getting close by. But I hate to take medicines. I rather go for exercise. Okay? So, there are some medicine you take, they
like metformin.
Metformin is one of them. Okay, it does not actually control the insulin level. It inhibits the glycogen breakdown, the glucose. So it's different mechanism. So not only insulin, correct? There are other pathways you can control. So your blood, if you cannot get down glycogen, your blood glucose level is low. So that's but it has a lot of side effects as well. So there is, I think people are trying, it's not successful so easily, that if you can supply the beta cells to the patient, okay, if you can culture the beta cell in vitro, the human cell line, you can culture the stem cells and allow them to differentiate into beta cells. And if you can give the beta cells inject into the body, it goes and sits in the pancreas and starts to make insulin. But I think some of these are not too far away. In mice it works, but it does not work so well in human for various reasons. So stem cell therapy is one of the promising therapy is coming out. So read some of these for you. I think we have gone over this. This is the structure of epinephrine. It comes from tyrosine, correct? So this part completes the gluconeogenesis and glycogen synthesis. And now we go to the next one. I think photosynthesis. I'll start, but actual photosynthesis will be in the next class. Okay. Okay. Photosynthesis. So I'm sure all of you have studied photosynthesis, correct? In the high school, that you put a plant in the sun, correct? And they are very smart, they keep making glucose. I wish we could do that. Then we don't need to eat. Correct? Then we could go, maybe 1 hour sun bath is good enough for the whole day. Maybe someday transgenic human with some photosynthetic gene. Correct? So basically what they do is capture the solar energy, the photons, capture the solar energy and convert the solar energy, capture the electrons out of the solar energy to convert carbon dioxide into glucose. Okay. The solar energy, with the help of solar energy, capture the electrons in the form of NADPH. The electrons from the NADPH is utilized to fix the carbon into glucose. So this happens. So this is the reaction you studied in high school. 6 CO2 plus 6 H2O, 6 H12. Correct? These are the high school chemistry. 10 to the power 11 tons of carbon dioxide are fixed global per year. Okay, it's interesting. Solar energy is coming. Lots of plants, lots of energy, lots of carbon dioxide is fixed in the form of sugar. Right? Many years ago, I had the opportunity to listen an ecologist, very famous ecologist in our biology department. No, he's not in the biology department. He was a visiting speaker, seminar speaker. His whole life is spent in ecology. Yes, very interesting because ecological diversity, correct? How it controls total. They don't talk about one molecule level, but they talk about if a particular organism is disappearing, how it affects the food chain, how it can affect this thing, correct? We eat so much of the ocean fish, correct? We catch all the crabs, we catch all the lobster, we catch all the sardines in the ocean, but this affects the ocean ecosystem. A lot of the big fish like whale, they are slowly disappearing, correct? A lot of the big animals, they are slowly disappearing. And when the dinosaurs would have lived today, we would not be living if they live out. Okay? But, you know, everything has a consequence. Global warming is one of the concerns. How many of you support global warming? I mean, all of you are contributing. Correct? All of you are contributing more now because every day you are driving car. Correct? Now, how many of you agree that there is global warming? Some of you did not agree. Correct? Why you don't agree?
Well, I agree.
Oh, you agree, but I did not see the hand. Okay. Is there anybody who did not agree? Well, I don't agree. So there is a controversial. We believe, I mean, everybody likes to believe. I don't want to talk about politicians. Okay, everybody likes to believe that there is a global warming, because we are cutting down all these trees, driving fancy cars, correct? And all kinds of stuff. Are you out of time right now? Okay. So, but to me, maybe it is a part of the evolution, right? It's not? It's not. You may be right. You know, the solar system is rotating, and it's a big universe. We are just tiny bit of planet existing in the whole universe. If you think actually, we really don't exist. Correct? If you think about the whole universe, how many of you have gone to our planetarium? You see a planetarium? You should go sometime. They show some telescopic pictures. I mean, the galaxies, the Earth does not exist. It's a tiny point. Correct? It does not matter how we work here. Eventually, all this energy could have lost and so on. So I think, to me, it's a controversial topic. If you have real global warming or not, that does not mean that I support cutting trees. Okay. I am against cutting trees, against driving cars, but it's a controversial topic. But the point which I was trying to make, whatever the reason, the world temperature, Earth temperature is increasing. Tiny. All this ice is melting in the glacier, correct? So this increase, tiny amount of increase in temperature has a huge impact on the carbon dioxide fixation. Why? Why you think it is happening? So we are plant and animal, we have all this respiration going on, correct? Respiration is nothing other than some chemical reaction, breaking down molecules into carbon dioxide, correct? So if you increase the temperature a little bit, the rate of respiration goes high. So you are breaking down a lot of plant or fixed carbon into carbon dioxide. And apparently, you are showing some statistics that if you have 0.5 degrees Celsius increasing temperature, how much carbon becomes carbon dioxide. So basically, we are depleting the stored energy in the form of carbon dioxide, right? So you are losing, so plant is trying to fix this carbon to food which we consume. But if there is a global warming, whatever the reason it is, right? We are losing this fixation. Eventually, people are going to suffer because we don't have this carbon mass content in Earth. Correct? It's all human become volatile carbon dioxide. Correct? Plant and animal. So this is very interesting in terms of ecology. So I support not cutting trees because correct, we can fix more energy, and that's what the plant does. I think next class we'll talk that how plant stores or captures the solar energy. Please return the exam.